Hi, I am Joonhyung Kim, and this is the presentation for Fourier optics. I'm going to talk about Fresnel diffraction and Fraunhofer diffraction. This presentation is divided into 4 parts. These are contents of my presentation. First, I'd like to explain the Fresnel and Fraunhofer diffraction theory briefly. Then we will move on to MATLAB simulation about 2 diffraction patterns. I made 2 different cases for each diffraction. Lastly, we are going to look at the summary of results. To explain the Fresnel diffraction, let's start from the Huygens-Fresnel principle in rectangular coordinates. The Huygens-Fresnel principle can be written as equation number 1, and R01 written at equation number 2 is given exactly in rectangular coordinates. Then there have been 2 approximations. One is the approximation inherent in the scalar theory, and the second one is the assumption that the observation distance is much bigger than lambda. So we can rewrite R01 like the equation number 3. The Fresnel diffraction means the Fresnel approximation to diffraction between 2 parallel planes. Equation number 4 presents the Fresnel approximation. And this equation is expressible in the convolution form like number 5, and here the convolution kernel is H as written at number 6. Another form of equation number 4 is found if the exponential term is factored outside the integral sign, the principle then written at number 7. The Fourier transform of the product of the complex field just to the right of the aperture and a quadratic phase exponential. In addition to the Fresnel approximation, the stronger Fraunhofer approximation is satisfied, then the quadratic phase factor is approximately unity over the entire aperture. And the observed field strength can be found directly from a Fourier transform of the aperture distribution itself. Thus, in the region of Fraunhofer diffraction, equation is written like number 9. There are observable differences between Fresnel and Fraunhofer diffraction. In Fresnel diffraction, the viewing screen and aperture are located close together. As the separation between the screen and the aperture increases, the image of the aperture becomes increasingly more obstructed. In Fraunhofer diffraction, the viewing screen and the aperture separated by a large distance. As the separation increases, the size of the pattern changes, but the shape is not changed. Chapter 2 and 3 is about MATLAB code explanation about Fresnel and Fraunhofer diffraction simulation. First MATLAB simulation for Fresnel diffraction is square aperture. In MATLAB, define the function named square aperture. The variable a means Fresnel number for diffraction, and I generated xy points in range of this. Then I used Fresnel functions as Fresnel number. Next variables zx and zy mean complex field distribution, and f means intensity of wave field. If Fresnel number is lower than 1, variable the intensity f needs additional computation. Finally, the MATLAB function makes images of square root f at xy plane. To make video of patterns, varying the Fresnel numbers so that we can see the diffraction patterns depending on the distance from the aperture plane. This is the result of the field diffraction at specified distance. Let's see the video first. This video starts at far field to near field. The images of the right side is diffraction patterns at different Fresnel number. As you can see, the Fresnel number increased. The intensity of wave field changed uniformly. Next MATLAB code is for designed aperture. I set up the input parameters like wavelengths and Fresnel number and initial aperture size. In this function named Fresnel image, the result varies depending on the distance z, the distance between aperture and observing plane. Use the MATLAB code presented at right side. I could make my own aperture by using drawing board application. I wrote the initials of my name KJH and covered the letters in a box. After a few steps, an aperture is completed. In PNG file, black part means the whole of aperture. In next step, we have to define convolution corner and intensity of wave field. And then finally, the function returns image of intensity distribution at distance z. I used same code for making video. This is the result of simulation. The aperture is about 2 mm wide and 1 mm long. Let's see the video about intensity distribution about distance. This video starts from near field to far field. During the video, an unusual pattern appears, but I'm not sure you'll agree that the pattern represents my name perfectly. Next item is Fraunhofer diffraction simulation. As I showed before, now we can use PNG file as an aperture. I brought a Korean traditional image, and for using this as aperture, we need invert the matrix. We can get the diffraction pattern simply as a result of fast Fourier transform of the aperture. The left picture is aperture made by inverted matrix, and the right side is diffraction pattern. In Fraunhofer diffraction, the distance from aperture is already considered very long, so there is no reason to change the distance. Then I changed the aperture and observed the change in the diffraction pattern. Using this code, we can make the two pictures overlap and move across each other. Let's see the video. We can see the stripe pattern is moving through the diffraction pattern. This is the same code that I just showed you. Let's change the XOR function to OR and check the difference. This is the summary of results. I designed square aperture and KJA aperture for Fresnel diffraction and simulated them by changing the distance. And I made the lotus aperture and moving aperture for Fraunhofer diffraction. This is reference list for my presentation. Thank you for listening.